The main idea of Lab 3 was to find the mass of a mystery object inside of a system that appears to be that involving a star and a black hole. Here we'll be using the gravitational force equation, which states that the net force is equal to the gravitational constant times the mass of the star times the mass of the black hole divided by the radius squared. Now here, all equations are going to be involving magnitudes, so the magnitude of the net force is going to be used instead of the net force vector. Now, the gravitational constant is equal to 6.7 times 10 to the negative 11, and we can derive this equation shown here to equal to the mass of the black hole with the rearranging a few variables. This is the equation we're going to be using our tracker, or excuse me, VPython data, so that way we can find the mass of the mystery object, which is potentially going to be a black hole. So this black hole is equal to the net force vector, or the magnitude of the net force vector, times the radius squared, divided by the gravitational constant times the mass of the star. Now, because we are going to be using momentum in the Python data, we're going to set the FNet equations equal to the change in momentum. So the FNet here is equal to the change in the momentum divided by the change in time. And then FNet perpendicular is equal to the change in momentum perpendicular. And FNet parallel is equal to the change in momentum parallel. We're also given, through using Newton's second law, that the change in momentum is equal to the change in momentum perpendicular plus the change in momentum parallel. And we can rearrange this equation to find the change in momentum perpendicular, which is going to be equal to the change in momentum minus the change in momentum parallel. So if we pull up our VPython data, we go up to the very top, we see that with the constraints given from the web assignment, I have rearranged the mass of the star to 1.989 times 10 to the 30th, and then the black hole potentially is going to be equal its position is going to be 3 times 10 to the 10th, 2 times 10 to the 10th, and 0. Delta T has been rearranged to 86,400, and the gravitational constant I added myself, so that way we can correctly find the mass of the black hole using the equation previously shown. So we use this information to find delta x, which would be the change of position, delta y, the change of y position, and the x position velocity and the y position velocity. We also use a few more equations shown here to find the initial velocity, the final velocity, the initial momentum, the final momentum, and then also the change of velocity and the change in momentum. Now here we're given that the change in momentum is equal to the change in momentum divided by the change in time, and FNet is equal to dp dt, which was previously stated on the document shown. We also find that FNet parallel is equal to dp dt parallel, and perpendicular is equal to dp dt FNet minus dp dt parallel, which is the FNet parallel. So FNet perpendicular is equal to dp dt perpendicular. Now, just going all the way to the bottom and plugging in all these constraints shown, we can see that the black hole mass is equal to the magnitude of the FNet force times the magnitude of the star position minus the black hole position, the change in the radius, squared, divided by the gravitational constant, which I created myself, times the mass of the star. Now, if we run the coding, we see that as the star gets closer and closer and closer to the black hole, we see that the forces increase tremendously due to the how close the star is to the actual black hole. This is because the radius gets so small, it is not being divided by much magnitude given. So we can see here that the parallel force is going to be equal to the black vector shown here because it is parallel to the motion that is being moving in, and the perpendicular force is shown as the blue arrow because it points in towards the angle that it is turning at, and the yellow vector arrow is the overall net force pointing always towards the black hole. Now, as we can see from the data shown here, the mass of the black hole we have found to be 3.98 times 10 to the 31st. Now this is a much larger value than the mass of the star, so this means that it will be much harder to get the black hole to move towards the star due to the massive amount of mass that this object has. So the star's velocity will always be much larger than the black hole's velocity. Now, what does this mean? How is FNet perpendicular related to FNet parallel, and FNet different from dp dt perpendicular, dp dt parallel, dp dt overall? The net force is different from change of momentum in that the net force caused the momentum change. This fundamental principle is explained through Newton's second law, which states that F net times delta T is equal to the change of momentum. F net is also defined as all of the forces overall acting on the system as opposed simply to the change of momentum. So, what if the black hole was changed? What if we got rid of the black hole that was there and added a different one? Assume the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. So to find the mass of the new black hole, all we would do is the same thing. We would just go about finding the mass with the same coding and formulas previously shown. The only change would be the magnitude of the net force in the code. It would still be the same coding, but the magnitude of the net force in the coding would be different due to the mass of the black hole changing. Now, this is assuming that the black hole's new mass is different from the original black hole mass. But assuming that they could potentially be the same, the result would be the same as well.